Last lesson, Unit 5. Let's see where this goes. So, applications of exponential and logarithmic equations. So yeah, there are areas where the letter E, natural logs, and just regular old logs actually are useful. Here's one. How many years will it take to double your money if you invest in a fund with 7% interest rate compounding continuously? Now that's a whole different idea, but this formula right here is the formula for compounding interest continuously applies. So they don't give us how much we invest, so that's a little bit confusing. So we're kind of free to say, okay, we're going to let this, the initial investment, remember this is an exponential function, this is like f of x equals a times b to some power. It's just fancy. So if we say, hey, our initial investment, let's go ahead and make that like $10,000. Wouldn't that be nice to have that much just sitting there where we can part with it and hopefully it grows? But it's saying double your money, so the amount over time, we'd say 20,000. Now I could put $1 here and make this 2. So it doesn't matter as long as the relationship is true. That letter E is our B in our y equals AB to the x. And then the rate is 7%, so it's 0.07. And it's asking us how many years. So it's saying find t. Notice where our variable is. It's stuck up in the exponent. So we got to solve this. Just basic math 101. Divide by 10,000. Divide by 10,000. So that would be 2 equals e to the 0.07t. Well, wait a minute. How do I do this? Well, this is where I'm going to slap a natural log on this side, natural log on this side, 0.07t. I now can bring that into the front. Notice what this is. It's 1. So I get the natural log of 2. Let me find out what that is. So natural log 2 is 0.69, we'll call it, equals 0.07t. Yeah, times 1, but we don't really need that. 0.07, 0.07, and this is telling us how many years. 0.69 divided by 0.07, as long as I didn't hit a button wrong, approximately 9.85 years it's going to take us to double our money. So I would say it's well worth it. All right, as you can see, new little section, they're going to give us kind of a shook up version of our exponential function. So we got our a times b to the x power. So they're going to like mix it all up, see if we can't manipulate rules like this, where the bases are the same and you're multiplying, you add the exponents. And recall that if you have something like this, you might be tempted to go 2 times 2 and make that a 4, but no, the base does not change. So keep that in mind as we go through this. One thing to keep in mind also, if I have that, I could break it into this, which I could break it into this. So you got all these creative ways to break something else down this way. And that's what we're really going to use. But the stuff gets a little weird. So it starts out with a pretty easy problem. If we take a look at this, and we would break it down into 3 cubed, and let's see here. Oh, I think I wrote the problem down on the first wrong on the first one. There we go. Sorry about that. So the reason I knew that I wrote it down wrong is I see this addition. My original said multiplication. And the only way we can turn this into the product of 2 is if this is addition, because I got 3 to the third times 3 to the x. And see, now I'm heading in this direction. But when they were times, I would have had to gone like this. And that's not really going to help me get this direction. So I wrote the problem down wrong, and so these are self-made to break it up into situations like this, which is 27 times 3 to the x power. Here's my a, here's my b, here's my power. So that was supposed to be the easy one if I'd have written it down properly. So now we got this situation. Like, okay, wait a minute, I have a 10. Can I make 10 times 220? No, 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 no. Not with this weird exponent here. If that was a 1, then of course you would. But I got to take that 10 and try to create a 2 so I can manipulate it. So I'm going to go 5 times 2 to the first times 2 to the 2x plus 3. And now I know that these are common bases, so I'm going to add those exponents. So I would get 5 times, now I can add these together, so I get 2x plus 4, times 2, there's my base, to the 2x plus 4. Now you might be thinking, that doesn't quite look like this. Well, technically, you could say you're done. But what the pre-calc homework assignment and expectations are is that you clean this up to the best of your ability, where you try to have one thing up here. So I would say, hey, nice job, you're pretty much getting it. But if I take a look at this, and I say, isn't that the same thing as 2 to the 4th times 2 to the 2x times 5? 2 to the 4th is 16. 16 times 5 is 80. So your book is going to have 80 times 2 to the 2x. And that's where they're going to want you to finish. So, little tricky. You got to keep moving stuff around. Again, by definition, you did follow the instructions on that, but you can also keep going. So think about an ACT, SAT. What if this is option A and this is option B and then C is both A and B? That's where you're going to need to know to keep going. So what's the right answer? Well, open your mind up to just exploring the idea of, not quite done yet. I can still manipulate this. So with that in mind, this one's going to be even trickier. So let's tackle it. With these. All right, so I hope you can see that, get into the habit of thinking, okay, 24, somehow I got to pull a 3 out of there, and that's pretty easy. 8 times 3 times 3 to the 3x minus 4. Now there's an invisible 1 there. I'm going to concentrate here first, because I see I got common bases, so I got 8 times, and I'm going to add these exponents here, 3 to the 3x minus 3. Here comes a twist. I'm going to keep concentrating on this. And again, this takes us back to, aren't we done? Because it really does follow this. But technically, they only want one. Basically, you're not done until you can create where you have one variable exponent. So, we take a look at this and we go 3, I'm going to make it to the negative third times 3 to the 3x, because this is the same thing as that stuff in the box, times 8. Now this is just 1 over 27, so I get 8 over 27 times 3 to the 3x. And now I'm really, really done, because this follows the definition of an exponential function. So, mess around with those, see how you do. All right, you guys, this is your final little lesson of Unit 5. We are getting to the end of the trimester. So, concavity review. Now, there's different theories out there dealing with slope and how to determine concavity. It's very simple at the end of the day if you just boil it down to these rules. Concavity down, I call it the roller coaster rule. Remember, the wheels are stuck to this roller coaster. As you're moving to the left, obviously your roller coaster cart's going down. But if you're going to the right, it's also going down. This would pass the test for concavity down. The opposite is true here. Concavity up. Roller coaster, I'll put the wheels here, but you get the idea. As I move to the left, going up. If I try to move to the right, it's also going up. That's concavity up. Pretty simple. Then they're going to give us some of these reciprocal functions. We have to be careful with the domain. X cannot equal 0, so we know that right here. Now I've already went ahead and plugged a few things in, but I'll show you what I mean. Put an easy one, 2. That'd be 4 minus 2 over 2, which is 2, 2, 2. So if I take a look at this, but I first should look at this and just realize that this is my asymptote. X cannot equal 0. So it's going to approach it, but it's never going to touch it. So negative 3, 1, 2, 3. Negative 2.3 would be right about here-ish. And then negative 2, right here. And then negative 1, 1 would be right here. And we kind of see what this is doing. Now we could plug in a lot more, but now we just have a general idea of what that looks like. So now let's go on to the positive. 1, negative 1, 2, 2, 3, 2.3. So 3 would be 2.3, which would be right about here. And as you can see, this one's kind of going like this and like that. Okay? And so here we go. We take a look at this and go through our list. Is it concave up? Well, so if I move to the left, it's going down. If I move to the right, it's going up. So neither of these are true because it doesn't follow these rules. So now the tough question, in my opinion, is it even or odd? Well, remember, if it's even, it's going to be a reflection over the y-axis. So if I focused on this one, and I spun this 180 degrees, would this graph lay right on top of that one? No, you can see it. How do we know if a function's odd? Well, that's where if we like stuck a nail right in there, we took our paper and we spun this one right here, 180 degrees. Would this one lay right on top of that one? I wish I had a piece of paper and I would have thought it out better. But as you can see, if I spin this one around that origin, this would actually lay right on top of that. This portion would go 180 and would lay right on top of it. So we're like, yes, that would be considered an odd function. That finishes Unit 5, you guys, so good luck on your homework.